Every image you are seeing was generated by AI, and one of the key ideas behind it is the diffusion model. In 2020, Ho, Jane, and Abil published DDPM. I implemented it from scratch, and the training loop was only 3 lines. Add noise, predict that noise, and calculate mean squared error. The loss was going down, so everything looked healthy. But the generated digits were blurry, rough around the edges, and sometimes impossible to recognize. Even stranger, the reported loss would suddenly explode and then recover. I eventually found 2 different kinds of problems. One was a logging mistake on my side. The others were hidden in the mathematical assumptions and the experimental details of Appendix B. I will follow the actual debugging path and connect each engineering decision back to the equation it changes. Start with the 3 lines. The first line takes a clean image x0, samples a random time step t, and constructs the noisy image xt while keeping the exact Gaussian noise epsilon that was added. The second line gives xt and t to a unet and asks it to predict epsilon. The third line compares predicted noise with the true noise using mean squared error. The network is not directly learning to draw a digit. It is learning which noise vector was mixed into the image at every possible noise level. That single interpretation gives us a common reference for the schedule, the sampler, the loss, and the architecture. The time index t tells us which diffusion step we are on. Beta t controls how much new variance is injected in that step. Alpha t equals 1 minus beta t, and controls how much variance survives from the previous state. Both coefficients appear under square roots because a standard Gaussian is multiplied by a standard deviation, while beta and alpha describe variances. One forward step is xt equals square root alpha t times xt minus 1, plus square root beta t times fresh Gaussian noise. If the image is standardized and the new noise is independent, the 2 variance contributions add to 1. This keeps the marginal variance controlled. It is a statistical statement, not exact conservation of pixel energy for every individual image. Expand the one-step equation repeatedly, and the alpha terms in front of the original image multiply together. We call that cumulative product alpha bar t. In code, Torch Comprod computes exactly this sequence. A linear combination of independent Gaussians is still Gaussian, so all previous noise terms collapse into one Gaussian. The original image contributes variance alpha bar t, and accumulated noise contributes 1 minus alpha bar t. Training therefore does not need to execute t forward steps. Each batch samples 1t and constructs xt directly with the closed form equation. This is why DDPM training can be efficient even though generation may call the network 1,000 times. Constructing a training example takes 1 tensor operation. Why does the derivation end with 1 line of noise mean squared error? The exact probability of a real image under the model is difficult to compute, so DDPM optimizes a tractable evidence lower bound. During training, we know both the noisy image xt and the clean image x0 that produced it. That makes the conditional posterior for xt-1 analytically available. The model defines its own reverse Gaussian and tries to match that posterior. Kullback labeler divergence measures the difference between those distributions. Once the variance is fixed, the Gaussian KL term becomes a weighted squared error between their means. Expand the means, and that difference is proportional to true noise epsilon minus predicted noise epsilon theta. The authors then remove the time-dependent weight to obtain L simple. This is an empirically motivated reweighting, not exactly the original evidence lower bound. My log jumped from about 0.02 to 0.425 at epoch 20. At epoch 93, it reported 1610. My first reaction was that training had completely exploded. Then I inspected the logging code. At the end of each epoch, it printed loss.item from the final batch only. Random variation in one batch had been mistaken for the state of the entire epoch. The real fix was to record epoch mean loss separately from final batch loss. The next diagnostics should include gradient norm and loss buckets for low, medium, and high noise levels. Gradient clipping can protect against an unusually large update, but it cannot identify the cause of a spike and it cannot repair a bad measurement. Logs are measurements of the system. If the measurement is wrong, every explanation built on it is unreliable. The paper increases beta linearly from 10 to the minus 4 up to 0.02 over 1,000 steps. This schedule determines how signal-to-noise ratio decays over time. If the starting beta is too large, the first steps destroy too much structure. If the ending beta is too small, Visible signal remains after 1000 steps, even though sampling begins from a standard Gaussian. With this linear schedule, alpha bar at step 500 is about 0.078. It is not close to zero. At step 900, it reaches roughly 2.7 times 10 to the minus 4. In signal to noise terms, step 500 is about 0.084, while step 900 is about 0.00027. The middle still contains some image information, only the final region is almost pure noise. After training, generation starts from standard Gaussian noise xt. At every step, the network predicts the noise in the current image. The sampler uses that prediction to calculate the mean of a reverse Gaussian and then injects randomness according to sigma t. The random term is not decoration. It makes each step a sample from the model distribution instead of always choosing only the mean. A full DDPM sample may call the network 1000 times. Model parameters stay fixed during one generated sample, but every prediction error changes the input to the next step. Sample quality therefore depends on more than single-step mean squared error. It depends on whether all those local predictions form a stable trajectory. Stochastic gradient descent makes nearby training checkpoints fluctuate. If generation always uses the latest raw parameters, visual quality can move around with those checkpoints. The paper maintains an exponential moving average, or EMA, of the parameters. After every update, the new copy is 99.99% of the previous average plus 0.01% of the current parameters. Sampling uses this smooth copy. EMA does not change the training loss, and parameters do not change across the 1000 steps of one sample. It averages nearby checkpoints along the training trajectory. Appendix B uses a decay of 0.9999. My EMA samples looked cleaner, but a valid visual comparison must use the same initial noise so that random seeds do not explain the difference. Reverse sampling must also choose the size of sigma t. The paper discusses two fixed variances, beta t itself or beta tilde t from the true conditional posterior. The curves are closed through most of the process and differ most when t approaches 0. At that point, the image is nearly complete. Using square root beta t as the noise standard deviation injects relatively more randomness into the final steps, while beta tilde becomes smaller near the end. It comes from the analytic posterior of xt minus 1 when x0 and xt are known, so the network does not need to learn it. My MNIST edges look cleaner after the change, but that remains an experimental observation. It needs the same checkpoint, the same initial noise, and multiple random seeds before we can call it stable. Every time step in the full evidence, lower bound carries a different weight. Low noise steps receive a high coefficient, while high noise steps receive less. L-simple removes those time-dependent coefficients, so uniformly sampled time steps enter the noise mean squared error with the same weight. Relative to the original objective, this increases the influence of parts of the middle and high noise region. On CIFAR 10, the paper reports an FID of 3.17 for L simple, compared with 13.51 when directly optimizing the variational bound. The first value is about 76.5% lower. One plausible explanation is that generation starts in the high noise region, so early errors change the remaining trajectory. But the table only proves that reweighting improved FIDI in that setup. It cannot prove this explanation is the whole cause. Once the objective is fixed, one UNet still has to handle 1000 different noise levels. The paper converts T into a sinusoidal time embedding and injects it into residual blocks, allowing the same feature layers to change behavior with noise level. At t equals 900, the input is almost pure noise. At t equals 10, it is close to a clean image. Those states require different prediction strategies. The downsampling path aggregates large-scale structure. The upsampling path restores spatial resolution. Skip connections carry earlier detail into the matching high-resolution layers. The output has the same shape as the input image, but every pixel represents predicted noise rather than a finished image. Samples in one batch are assigned different time steps so their feature statistics can differ. Batch normalization depends on the mean and variance of the whole batch. Group normalization works inside channel groups of each individual sample. It does not depend on other samples or on batch size, which makes it a better fit for mixed noise levels. Self-attention lets every spatial position combine information from every other position, but its cost grows with the square of position count. A 32 by 32 feature map has 1024 positions, producing more than 1 million attention entries. 16 by 16 has only 256 positions, reducing that matrix to about 65,000 entries. The original paper places attention at 16 by 16, making a concrete trade-off between global relationships and computational cost. The paper uses dropout zero point 0.1 for Cypher 10 and sets dropout to 0 on the larger L-SUN datasets. Tutorials often turn this into a fixed recipe, but it is only a hyperparameter tuned together with dataset size, model capacity, and training duration. EMA decay, gradient clipping threshold, attention resolution, and reverse variance are engineering choices of the same kind. The derivation tells us what each variable means. Experiments tell us which combination works for a particular dataset and model scale. Copying the paper settings is a sensible starting point. It is not a substitute for control comparisons in your own system. Now return to the title. What is a diffusion model actually learning? The score is the gradient of log probability density with respect to the sample. It points in the direction that increases log probability fastest. For one fixed clean image, the conditional score of its noisy distribution differs from the added epsilon only by a known scale factor. During training, averaging over many clean images guides the network toward the score of the noisy marginal distribution at each noise level. Noise mean squared error can therefore be understood as learning a family of local correction directions across T. The sampler begins with Gaussian noise, repeatedly queries those directions and moves toward high probability regions of the training distribution. The model is not learning one finished image. It learns local navigation rules that change with noise level. The same UNet can predict three common targets: added noise epsilon, clean image x0, or a rotated combination called V, given xt and t. The outputs can be converted into one another algebraically, but applying an unweighted mean squared error to each target creates different implicit weights across signal to noise ratios. So optimization difficulty and empirical behavior change. Classic DDPM predicts epsilon because the target comes from a standard Gaussian at every time step and connects directly to score matching. Predicting x0 is easier to visualize, but at high noise, the network must recover an entire clean image from an almost random input. The V-target rotates x0 and epsilon into a balanced coordinate and is common in modern diffusion systems. The parameterizations are convertible. Their training objectives are not simply identical. Bring the whole chain back together. The closed-form forward equation lets training sample any time step and construct a noisy example directly. The evidence lower bound passes through KL divergence and Gaussian mean matching to become noise mean squared error. Correct logging tells us whether training is actually unstable. The noise schedule sets signal to noise ratio at every step. EMA smooths the parameters used for sampling. Posterior variance controls randomness near the end. L-simple redistributes training weight across time. Time embeddings, group normalization, and attention help one UNet handle inputs ranging from almost clean to almost pure noise. What the model finally learns is a local correction direction at every noise level. Mathematics defines where that direction should point. Engineering decisions determine whether the network can learn it reliably. The training code and full derivation are linked in the description.